Now, you may want to log into the group again, or maybe you're already logged in. We have 37 students logged in, so only 31 participated, if anyone hasn't joined yet. So we would like to have as many answers as we could. 27 out of 33. 4 more should participate, 36. 3 more students. So let's have a look at the answer. The correct answer is D. Why the ball reaches to the same height? The explanation, we're going to see that during the upcoming chapters. So when we deal with the energies, 2 types of energy, gravitational energy and kinetic energy, that 82% of a student answered to this question correctly. Next question. Okay, 38 is good. When 38 answers, we look at the right answer. 2 more. 2 more answers, and the right answer is C. Okay, so that's an ideal situation, but in the absence of friction, when the ball is released, because it cannot reach the same height, it would roll forever. That's an ideal situation. So non-zero net force, everyone knows what the net force is. If the net force is non-zero, that is referring to the second law of the Newton. Okay, 10 more answers. 2 more answers, and that's it. We look at the answer then. Okay, the only wrong answer is B. Both A and C are correct, so B is the only wrong answer. And according to the Newton's law of the motion, if the net force is non-zero, the motion is going to change. It's not remaining as it is. So the non-zero net force is responsible for change in the motion. So next question. Anyone remember the right term? Okay, so you realize here the system is not an inertial reference frame. Because of the acceleration, the reference frame is the car is moving, the car has an acceleration. Because of that acceleration, the law of motion doesn't apply here. 89% got it right. All right, so it seems the truck driver didn't know about the law of the Newton, and when they packed the rock, they didn't know what happens when they brake. And the right answer is C. 97% got it right. Great. So this is very interesting. I would like to see how you perform with this one. B, 97% correct. And is this a change in the motion? First law of Newton, it says when there is a change in the state of the motion, if there is no external force, the motion remains as it is, either stationary or it doesn't change. Second law of the motion says what is responsible for change in the motion is external force. And we would like to discover, in this case, is there a change in the motion? So to answer the question, let's look carefully at this diagram. So the motion is described by the velocity. So first we have this velocity here, v1. Then we have v2, v3, v4. Just first question, how do you compare v1, v2? Are they the same? Are these two velocities the same? No. Why not? The magnitude is the same. So for a vector to be identical to another vector, 2 requirements. First is the magnitude. Second is direction. So in this case, which one is violated? Direction has been violated, right? So as long as the ball is resting against the cylindrical face, there is always a change of velocity, not because of the magnitude, because of the direction. So because of that change into the motion, there has to be a non-zero net force. And when the non-zero net force exists, that is the second law of Newton, right? And during that stage, there are going to be a net force applying between the ball and the surface. So for every individual instance, you have one contact force between the ball and the surface. That is when the state of motion is changing, but the minute it releases the surface, that contact force disappears. Everyone can see this? So once the ball is leaving the cylindrical face, the contact force or net force becomes zero. And when the net force is zero, what happens? Which law of the Newton? Zero net force, which law of the Newton is that? First one. So from that point forward, we should expect no change into the velocity. So is this a fake photo or what? Haven't you seen people performing that? So I assure you, C is not an option. It's a real photo. Spontaneously, suddenly, if that velocity is applied, or if the velocity is not constant, there is going to be an acceleration. According to the second law of Newton, there's going to be a non-zero net force. So when you apply the force spontaneously, the chances are you're going to lose your teeth. But when you apply this with a constant velocity very slowly, you only develop a zero net force, and that zero net force is something can be tolerated with that teeth. We are going to see this in upcoming lecture on the concept of momentum. Okay, the same truck, same driving force. The only difference is one truck is empty, the other truck is fully loaded. So what do you reckon how the accelerations are going to be different? The right answer is B, 63% got it right. And if you look at the pictures, I mean the picture is speaking for itself. Identical forces, the red arrows are of the same size. The black arrow acceleration, this one is larger. And why is that? Simply because of the smaller number multiplied by larger number equal to the larger number multiplied by smaller to keep the balance between two forces, because we know both forces are equal. So you have this fraction is smaller than 1. Here, apparent weight is 0, and like I said before, mass is a property of an object. It doesn't matter if that's Mars, anywhere in the deeper space, the mass remains the same. But something that changes is weight. Weight is the gravitational force. And this astronaut is orbiting, so the motion is a circular motion. With the circular motion, there's always a centripetal acceleration. This is a very tricky question. Okay, that is the right answer, but I want an explanation. All right? Anyone can explain. So this is a controversial question. 46% wrong, 55% right, but even those who got it right, can you explain? Yes. Force is the same. Force developed due to the hammer or due to the heavy, the force is the same. So why the hammer makes her to go quicker? When she is releasing the lighter wrench, the total weight is less. So if they are producing the same weight, because in the second case when she is releasing the hammer, she becomes lighter. According to the second law of the Newton, if the force is equal, and in one case you're dealing with a light system, that would accelerate higher. And if that accelerates higher, that means she reaches to the International Space Station faster.